Okay, so now let's address viscous forces. So here you have your state. I will use again the state, so I'm not going to redo everything. Okay, so here open, no, it is load state. There you go. FB, viscous. Okay, so here also remember to choose the right file. Okay, and there you go. So we have the state. This state is for viscous forces. We already did in Fluent. Now this is the OpenFOAM data set. Nothing changed. Okay, so let's revisit here our pipeline. So we read the case, all the fields. Grad U is the gradient computed in OpenFOAM. Remember previously we have it in Fluid, now we have it in OpenFOAM. You can compare gradients, OpenFOAM, Paraview. You will see there are slight differences. You will see this factor of 2, by the way. So yeah, I think let's work on that. So let me close here. We have the 2 windows. So let's go here. Extract block, internal mesh. We compute gradients here. Gradients are available. So everything is self-centered and using. And now let's do to my left, OpenFOAM, to my right. To my left Paraview, to my right I will put OpenFOAM. So here let's go Paraview gradient, first one, okay, and here it should be this one, okay. Let's change scales, minus 5, okay, and here to my right, let's put here would be OpenFOAM, which is grad U. Okay, so you have a function now to compute that. Hope you know which one it is. If not, probably somewhere in our channel there is a video showing that. And there you go. So as I mentioned, same issue. Okay, it's twice this one, but it's how it is approximated in Paraview. Okay. So that issue of the goal says, again, correct me if I'm wrong, or if you know a better explanation, just let me know. So see here that if I have this, okay, there you go. So same issue. So that being said, let's keep reading our pipeline. So grading, then extract surface, critical step. We mentioned that when you do this, and it's very important that now, let me go here, and I think I have this extract block. Look at that, I have an extract block there. Let me put it here to my left, to my right. And if I plot their velocity, it's 0. Okay? Recall that Fluent will already project it, but here in OpenFOAM is 0. But however here, when I do this extract block here, on my whole internal mesh, if I plot here you have the velocity. Okay, so very important, okay, steps to how to project the velocity, and to this matter also gradients and so on at the walls. Okay, so this is the step, extract surfaces, and you can confirm that the fields are exactly the same. No, nothing changed, just a projection. So let me put here P, and let me go here and put P as well. So as you see, pretty much the same. So if you are not sure, just compare. Okay, so we keep reading here, extract surface normals. Okay, now let me go here, leave it here. Surface normals, we need it, okay, and then we have the calculator. So in this one, we compute the vulture stresses, exactly same equation, you access the gradients, nothing changed. Okay, again, remember this issue with the sign, so on Fluent, I was multiplying by minus, here I don't put it, okay, to get the same convention as an OpenFOAM. Then next step, it is the result. So here it is 2, okay, this is the 2 of the gradient, dot the quantity as we did previously, okay, and to stress is the 2 of the gradient, no, it's not any 2 coming from here, okay, some people say that, no, it's the 1 of the gradient, so thing is the goal cells that I'm missing. Okay, in any case, so here we have the result, and split here, integrate variable, and you can have it there. So say that cell data, and let me access result, and there you go. Okay, so this will be X component of shear stress. There you go. So a little bit larger. Remember that we have that noise in the boundaries, we don't eliminate, we didn't remove them, but you can remove them if you want. I showed that, or probably I can repeat how to do that. And what I wanted to do is here, it was to, okay, so for instance, if I want to compute the other component that I think I already have it somewhere here, so yeah, it should be this one. Let me put it here, apply 323, should be here, there you go, 3023, okay, so a little bit larger. Okay, but doesn't, I'm not worried about that. I know the issues I'm having, so all this stuff there are influencing how I compute in that quantity and so on. Okay, you can keep doing the same with all the other quantities. Let me go back here to the original one, and you have the result there. And here in this case, no, it's just the comparison, no need to, okay, yeah, we can, let me split here, and here we have wall shear stress from OpenFOAM, okay, X component, and see that we have same scale, and visually speaking, okay, qualitatively speaking, we have the same, and if we go here, okay, we should have the integral also should be something similar, if I'm correct. Let me see if I'm computing that integral here. Should be cell data of what? I forgot. Okay, wall shear stress. And there you go. So OpenFOAM, and is giving that, so it's correct. Okay, so OpenFOAM, this is a little bit over predicted, the other one also, and that's it. Okay, so there you go. So this is how you compute your wall shear stresses. Just follow the pipeline, critical step, surface strat, and to also recap how to remove that, which is something that you will have in Paraview 6. When you do this operation here, you will get all this stuff now. So well, you say that you have all these patches that you extracted. No, it was here. All these patches now, and you extracted everything. But if you want to remove those, so remember that you have a filter here, alphabetical. This is a new filter. You apply here, you give it a name, and we'll subdivide using this angle. Then here, BTK regions, and each color corresponds to a different region. So now you can separate it. So you can take the long road that's selecting there, or this is one is just here using threshold. Okay, so let me use that one. Here, so this one I think is 0. Okay. There you go. And if I would recall, the small pi was 4. So let me apply this one here also, threshold. And there you go. I extracted the two of them, and now here I will have all my information. So you can put your velocity. So this also can be a little bit annoying because you have two. So what you can do now is group everything. And now when you group everything, you will have everything there applied. And then you can proceed as usual. So group, gradient view, you have your gradient there. And just to show you now also, let me put this one that we have graph view. And there you go. Okay, so we have OpenFOAM. No, I'm using the same here. Graph view. Here I need to use gradient. Gradient 0. Okay, and let me change the scale to -5. There you go. So recall that it is half. And this is it, okay? So now I separated it, that I remove those patches, and then since here are different from previous case, so probably I can visualize that pi line. Maybe I can have it here. Yeah, so see that previously the gradients, I had all that noise coming from that information added into my error. Something here also in the top, not much, but here also I think you have something. So by removing that, okay, now we reduce those errors there, okay? So at this point, we have all the steps, how to compute, we compare solutions. I don't need to open the Fluent to show you the color, you just can see it by the forces that you have there. So hopefully I had answered that question. That I find it very curious, why in the hell people wants to do that? And then I realized, yeah, probably you want to plot forces, compare something. I also did it a long time ago, but that's it. So that's all for forces. Next videos will be about moment, but you have the most important things here. Moment is very straightforward. So hope you enjoy it. See you next time. Bye.